Okay, now I'm pretty messed up. I guess I'll demonstrate the nested interval theorem because I skipped that last time. The picture there shows that how those A's and B's are lined up. All the B's are an upper bound for all the A's, and all the A's are a lower bound for all the B's. But we kind of have to demonstrate that. So let me give a proof of the nested, and I add the word closed intervals because it's important that those intervals be closed. Interval theorem. Okay, that nested closed interval theorem said that the intersection of all the INs equal to is not empty. So there's a real number that's in there, that's in all the intervals. And that's what Cantor used to show that he could come up with a map that misses a real number. Any one-to-one map from the integers into the real numbers misses a real number. So it can't possibly be onto. And so it can't possibly be countable. Okay? So let's see. The fact that I have that tower of inclusions, AN, BN, is contained in, and not necessarily equal to, A1, B1. And so that means that it must be the case, since A1 is the set of X that's between A1 and B1, the second interval. That means that AN is less than BN, is less than or equal to B1. So that shows me that all the ANs are bounded above by B1. Hence, B1 is an upper bound. For the set of all ANs. Okay, a set that has an upper bound has a least upper bound. So that set has a least upper bound. Let's call it R, and that's another way to write least upper bound is the supremum of all the ANs. Okay. R is going to be the thing that's in the intersection. And let's see. I need to do something else now. Because AN. Now I want to show that all the B's are above that R. So let's see. Here's the way to do it. ANBN is contained in A1B1. I already did that one, sorry. Let's see. A1B1 is the big one. Is contained in A2B2, etc. Is contained in etc. That means A1 is less than or equal to A2, is less than or equal to A3, etc. The funny thing about doing this next thing is I have to split it into two pieces. So we know this. Okay. So the bigger those number is, the smaller those intervals get. So notice that an plus k, bn plus k, is contained in smaller numbered set intervals. So that means that an is less than or equal to an plus k, and of course that's less than bn plus k, and that's less than or equal to bn. So all the ones for the n plus k's, an plus k's, are bounded by the bn. So we see I'm using this one and this one. Okay, so what I have so far is that an plus k is less than or equal to bn for all k's, for k equals 1, 2, 3, etc. But we also know that the a's are strictly getting bigger and bigger. But a1 is less than or equal to a2, is less than or equal to dot, 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 is less than or equal to an. And so they're all less than or equal to bn.
Why is that not like a strictly less than bn?
Because they just have to be contained in each other. So what I drew in the picture above, notice that when sometimes I don't make an increase. So for example, it would be okay if they shared a left endpoint. It'd still be a tower of things. And in fact, this one here, it'd be okay if they stayed the same for a few times. In fact, it could stay the same forever after that, and this theorem would still be a true thing.
Right. It makes sense that the bn plus k can be less than or equal to bn.
Right. And so can the a's.
But the an plus k we defined as strictly less than whatever bn plus k was.
Right. The intervals aren't zero length.
Okay.
That's why that one's true. Yeah, they're strictly. I guess they could be zero length, but I don't like zero length ones. The only time I ever think about this is when they're positive length intervals. Does the book allow zero length intervals? If they do, it would make a difference to this fact. Still be true. No. Huh.
If in the case that bn plus k equals bn, an plus k still has to be strictly less than.
Oh, I see. The book allows the book allows you to say a closed interval equal to the singleton a. Okay, so you're right. Maybe since that's allowed, I'll put a less than or equal to here. Some books don't allow that. An interval has to have a length. So then I have to make this a less than or equal to. Okay, so there's two cases here. I've got the an plus k is less than or equal to bn, and I've got all the a's before that bounded below an. So maybe I should make this, this would be true for k equals 0, 1, 2, etc. So all the a's are less than or equal to bn. That means that bn is an upper bound for all the a's. So Bn is an upper bound for the A's. 2. So let's see. Remember, R is the least upper bound. So R is less than or equal to B. All N. And so the BNs have a lower bound. So the BNs are bounded below. And now we know there exists a greatest lower bound. So the BNs from 1 to infinity have a greatest lower bound. And that's called the nth. And since R is one of them, R is going to be less than or equal to the nth of the BNs. And now we're done. That shows us that the R is in all the intervals. So the aha is that AN is less than or equal to R is less than or equal to BN. R is in all of them. For all N. So of course R is in the intersection. And that intersection is not empty. Here's any questions about that? I'm sorry I'm so flustered today by this stupid computer. Here's a remark. But what I showed you here is that the soup of the ANs, that's equal to R, that's less than or equal to the nth of the BNs. It's possible that, like those intervals get stuck at some point and they don't shrink anymore. That's possible and allowed. If there's a strict inequality here, so if soup AN equals R1, and that's strictly less than the nth of the BNs, make that less than sign in red. If that's a strict inequality, then the whole interval from R1 to R2 is in there. It's contained in the intersection. Okay. And the next theorem in the book, which I'm not going to dwell on because it'll be excruciating to do that again. Here's the next theorem. If the length of the intervals go to 0, then of course the intersection can only contain a single thing. So in the nested closed interval theorem, and here's how they say the lengths go to 0. If the nth infimum of the Bn minus Ans, that's the length of the interval, for n in n. If that's 0, and here's what you should think. We're going to talk about limits in the next section finally. That means that the limit, as n goes to infinity, of the length of the intervals goes to 0. That's what we're going to talk about in the next section. 3 points, next chapter, in fact. Then the intersection is a single point. Singleton. Okay. And that's not hard to do. It's just then you show that this inf is equal to the suit, and you only get 1 point in there. It's possible the inf could be the suit could be less than the inf, and then you get an interval in there. Okay, let's see. There was a couple things I wanted to do before I got started today, but I lost my train of thought. At the end of the last hour, we were talking about a set that belonged to itself, and I drew a blank and didn't think of the classic example. An example of a set that belongs to itself. I emailed it to you. Let S be equal to the set of sets that contain at least one element. There is a set that contains one element, namely, S is not empty. This is a remark. S is not empty. The set consisting of the empty set is in S, because it has only one element, namely the empty set. If you look at the axioms for set theory, you might wonder if there is such a thing. S is contained in itself. S is contained in S. And then you could monkey around and see, okay, find me a set that's not contained in S. How about the set of sets that have more than 2 elements? Or no, wait a minute. Anyway, you could think along similar lines and come up with a set that's not a member of itself, playing games like this. So Russell's idea wasn't totally wacko. The problem is if you start talking about the set of all sets, that's when you run into difficulties and the paradox. It's too big. Well, let's see. I also wanted to make a remark. I proved the uncountability of R. I was going to ask you a question. Why can't we use Cantor's idea to show that the rational numbers are uncountable? Any ideas? I could still, let's say I had a one-to-one onto map from the natural numbers to the Q, then I'd get a Qn, and I could choose an interval that's not containing Qn. Let's see, so here's I would get a Qn, and then I could even choose my rational, I could even choose the endpoints to be rational. This could be Pn over Qn and curly Pn over curly Qn. A closed interval that doesn't contain Qn with rational endpoints. And then I could do the closed nested interval theorem and get something that's in there. What's the problem, though, when I do that? Yeah.
You can make the thing in there irrational.
Exactly. It might turn out to be a square root of 2. So it's going to bomb because the intersection is going to contain something. Contains an R, but R might be irrational. Like the square root of 2. So that would make it bomb. I should also show you some. I should show you some examples about why we had to make those intervals closed. So here's some examples. Here's very easy examples. If I took in to be the open interval, say from 0 to 1 over n. Those are the open intervals, not closed. Then the intersection of those INs is empty. Doesn't contain anything. Let's suppose it contained an R. Of course, the R would have to be positive because all those things are positive real numbers. And you can eventually get a 1 over n that's less than that R. So R is not in there. So that's how you show it's empty. That was the Archimedean corollary. Okay, and the same example shows that if I took the semi-closed interval, 0 to 1 over n, including that right endpoint, its intersection is also equal to the empty set. So being a closed nested set of intervals is critical. For the nested interval theorem. I thought this might be a fun moment to explain why we are being so picky about these mathematical arguments. Picky and careful. It's because you can make big errors when you aren't careful. One of my favorite examples to talk about is, here's a question. Suppose you got a sequence of functions. So we have an fn of x. They're all going to be greater than or equal to 0. Okay, and their limits. We're going to talk about limits in the next section. The limit as n goes to infinity of fn of x is equal to 0 for each x. And the question is, you might want to know, is the limit as n goes to infinity of the integrals equal to 0? Let's make this an integral from 0 to 1. Well, you can come up with examples where you can make that fail. So the answer is no, for example. Let's see, I'll draw an example. I could make, let's see, I'll make the interval go from 1 over n plus 1 to 1 over n. That's a small interval. Here's 0. And then I'll make this thing gigantic. I want the area under here to be 1. So this h should be equal to 1 over n minus 1 over n plus 1. That would make that area be equal to 1. And this is going to be the Fn. Well, those Fn's, if you pick me an x, eventually the 1 over n's get less than x. And so they do go to 0 everywhere. And they're 0 at 0. So I mean, the function I'm drawing here is that there, and it's going to be 0 outside there, out to 1. So the value up here is this 1. And so the integrals are all 1, even though the functions at each point go to 0. So the area under that curve is equal to 1, even though all functions go to 0. And if I could even make these functions be continuous. I could make that area be 1, but I could make it a smooth bump instead of a staircase bump. I could make it a trapezoid or something that's continuous. So I could play games, and I could even make the Fn's be continuous and still violate this thing. So I could cook up continuous F. So that's why we've got to be careful. Sneaky, weird things can happen like this. I could cook up continuous. Oh, for crying out loud. Sorry. I could cook up continuous ones. I could make a trapezoid with a proper area 1. I'd have to make it go a little higher. Stuff like that. So that's why we've got to be picky and careful. Questions about that? I gave you Cantor's second proof earlier in the semester. And it's fun to talk about. So second proof that R is uncountable. I'll recap what I did. Remember, I assumed that there was a phi that was onto R, mapping the natural numbers to R. And I would write phi sub n is x sub n. And then I would expand these x sub n's in a decimal expansion. Let's make not just onto R, but onto, how about 0, 1. X would have a decimal expansion, so I could make it be D11, D12, this is a digit, D13, these are the digits, D14, dot, dot, dot. That's a decimal expansion. X2 would be D21, D22, D23, etc. Dot, dot, dot. I'll do one more. D31, D32, D3, dot, dot, dot. And Cantor's brilliant idea was I can make something that doesn't get hit if I pick a D1 that's unequal to D11 and pick a D2 that's unequal to D22 and a D3 that's unequal to D33, etc. Then the real number that's dot point D1, D2, 3, etc. does not get hit. By feed. And so you can't count the real numbers between 0 and 1. And of course, therefore, you can't count all the real numbers either. It's uncountable. That was Cantor's proof. And I slid a little technicality under the rug when I did this the last time. This section of the book talks about it. The technicality is that it turns out to be true that real numbers have a unique decimal expansion, but there's a case you have to rule out. Namely, if it repeats, if it's 0.999, so here's a technical point that I swept under the rug. And it's in this section of the book, technical point. See the section in 2.5. It's called an optional section. I think it's worth reading. Are decimal expansions unique? They almost are. You've got to think about it a little bit and rule out repeating ones, repeating nines. Are decimal expansions if they are, then this thing definitely works. To motivate this next thing, let me, here's my favorite example. Let's take 3 is less than 4. 3.1 is less than 3.2. 3.14 is less than 3.15. 3.145, guess what I'm doing here? Less than 3.146. 3.1459. This is pi. What? 3 point? Yeah, 146. Anyway, etc. This is going to be 2 here. When I was an undergrad at Michigan, all the engineers knew pi to 16 places. And then I went to MIT, and everybody around me knew pi to 40 places. It was weird. If you ever went to the beach with a bunch of MIT students, they'd start writing pi in the sand and see who could write the longest string. Anyway, the thing here is I'm doing numbers on the left, notice they're an increasing sequence, and they're all bounded above by the stuff on the right. So it's very much like the nested interval theorem. And so, in fact, those decimal expansions, if I took the soup of that left-hand side, that soup would be pi. And of course, pi is irrational. It's a very famous number. The proof of that pi is irrational is really tricky. It doesn't. No, it's not terribly tricky. There's some papers out there that do it in 2 pages using clever ideas, including things from ODEs that are fun. But it's an irrational number, just like the square root of 2. And that's, in fact, it's also, since it's irrational, it's never repeating. So the soup of the left-hand column and the inf of the right-hand column are the same point, and that same point is pi. So the soup of the left column equals pi equals the inf of the right-hand column. Okay, and that you can convince yourself that those, if as soon as you get one number that's different in a spot, those things are unequal. This one's definitely bigger than this one, and they're definitely unequal, right? But here's the technical point. There's a case where if I had repeated 9s, that's actually equal to 1.0. You probably saw this in high school or junior high someplace, did you? Yeah. And the way I like to think about that is in terms of, everybody likes to think about it in terms of geometric series. 1 plus r squared plus r to the, let's do r to the n. Let's call that s sub n. That's a geometric series. And you learned somewhere probably that if I multiply that geometric series by r, it looks very similar. The 1 times r I'll put over here. The r times r I'll put here. The last one would be r times r to the n. That would be r to the n plus 1. And now if I subtract the top one from the bottom, I get 1 minus r times Sn. The 1 hangs up here on the left-hand side, but then all this middle stuff cancels. And everything cancels except the last one hangs out, and I get a minus r to the n plus 1. And so the sum of a geometric series, famously, is 1 over 1 minus r over minus r to the n plus 1 over 1 minus r. Okay, and 0.99999 until I get the nth 9. That's equal to 9/10 plus 9 100ths plus 9 1,000ths plus etc. 9 over 10 to the nth. And now that we know this formula for the sum of a geometric series, that would be 1. Oh, let me do. I'll do it. I'll pull out the 9/10. That's 9/10 times 1 plus 1 over 10 plus 1 over 10 squared plus dot 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 plus 1 over 10 to the n minus 1. Okay, and that's, now I'm going to use the sum of a geometric series. This geometric series is 1 over 1 minus 1/10 minus the n plus first power of 10, so that would be 1 over 10 to the n back over 1 minus 1/10. Okay, that first thing is 1 over 9/10. So that's equal to 1 minus 1 over 10 to the n. Okay, and as n goes to infinity, that is going to be really close to n. I mean, it's going to be really close to 1 as n gets bigger and bigger. And in fact, if you let that n go to infinity, then you can see that those things, let's see, these things are an increasing sequence. So 0.9, 0.99, 0.999, ... is an increasing sequence. Its sup is equal to 1. Its supremum equals 1. And in fact, that, you know, when you were talking about defining the square root of 2, this thing defines 1. Its limit is 1, and so it's another way to define 1 as a limit, like we define the square root of 2 as a limit. So 0.99 repeating is equal to 1. Now that we understand the completeness of the real numbers. Anyway, if you toss out repeating 9s, then you get a unique decimal expansion, and the book demonstrates that. Toss out repeating 9s in the decimal expansion. So an example of doing that would be example 0.1234999999999. You would use 0.123500000 instead. Then the decimal expansion is unique. And it's better to use the binary system than the decimal system, because then it's more transparent that you get uniqueness. So the book does it for the binary expansion, 0s and 1s. You don't have to worry about 1 through 8. Okay. A fun fact that mentioned also is that a decimal expansion is repeating if and only if it's a rational number. I assume you saw that somewhere in high school also. Any last minute questions about